Hi everyone, welcome to SciPy 2020. My name is Fatma Kalju and I will be chairing this current session with you today. And we have with us the presenters for the talks listed in the schedule for this session. And this session is machine learning. Before we start with our first speaker, I want to go over a couple of logistics. I will invite each speaker to the screen in the order that they are listed on the schedule. We will have about 5 to 6 minutes for each speaker to answer your questions. And if we have time at the end, we will have a moderated discussion where you can ask more questions to the speaker of your choice. You can click the Ask a Question button on your screen and you can upload a question if you want it to be released. I see that there's a great crowd in here today, so I'm expecting a lot of questions. So if you really want one question to be asked, please upload the question and then we will try to answer as many questions as we can. With that, I would like to invite our first speaker, Andres Miller, whose talk is titled Double Automatic Machine Learning with a Human in the Loop. And then let's see the questions.
Thanks, Andy.
Okay, question for Anders, or if you want to go over your talk briefly, you can do so as well while we are piling up some questions.
I mean, maybe just very briefly can you maybe mute yourself if I'm talking, because I get very heavy echo. Okay, I'm not going to answer the first question, but I still get a lot of echo. So, Hassan, if you missed the talks are recorded, and you can still watch them offline.
Okay. Okay, let's see the first question. How do I pass the Turing test? I'm absolutely not a robot. And I mute myself to see if the echo is going to go away.
Yeah, I don't think the Turing test is a good measure these days. So it's probably pretty easy for things right now to pass the Turing test, and I think people have shown that it's possible. So maybe we want some other definition of intelligence. But it would really be great if we could work on the echo. But
let me figure it out.
Never mind, I fixed it. Apparently, if you have to crowdcast open into Windows, then that gives you terrible echo. Okay. Any questions about the talk? So Dabble was about doing very simple, very out-of-the-box automatic machine learning. So there's one question, did I compare with other packages? And no, that's definitely on the to-do list. There's an AutoML benchmark. That's a pretty well set up benchmark, which is a very good way to really compare different AutoML systems. However, this is designed for a little bit longer runtime. So what you really have to do is you have to go, how good is a certain package at a certain runtime, because different packages are optimized for different time frames. Okay, so.
All right, there is another question. It goes, in the talk for the automatic classification step, you said you use always fast things like naive Bayes, etc. Presumably there are choices and trades-off here. Can you talk about that?
So this portfolio is actually not optimized. So the rest of the portfolio was optimized, and I talked through the optimization process. So for naive Bayes ones, they do have a parameter, and I think I have. It's just set to the default, but the thing is, computing naive Bayes takes the same amount of time as scaling the data. So I'm not sure what trade-off you mean. Do you mean a trade-off in terms of tuning the parameter, or what to run? So the one, just running the algorithm is just very, very quickly compared to any of the other algorithms. And the same is true for decision stumps. So this is basically a single pass over the data. And yeah, so I think it's pretty safe to just run these and to run even multiple of these. Of course, you can't run all possible configurations, but it's just sort of things that a trade-off that is meant to run really fast, but also potentially give some baseline results. Oh, the question, I guess, was what is obvious? And the obvious is, in a sense, that it's very, very fast. And so that's mostly true for Gaussian naive Bayes and very shallow trees. Logistic regression is maybe not that obvious, but it's something that you should definitely run. It's going to take longer. And actually, I should configure this better, and they would be like. So I didn't. This is just a heuristic. Basically, the way it is done right now, it runs with very strong regularization, and this makes it faster. But I actually should optimize the logistic regression run better.
Okay. The next question that has a lot of votes is: are you planning to include some of double utilities into scikit-learn?
So. A couple of them already are. So the plotting stuff is probably not going to go into scikit-learn. The building blocks are like the plotting of work curves and so on. We recently added to scikit-learn. Successive halving is also going to go into scikit-learn. But a lot of dabble is like heuristics or how to put together like the column transformer and so on. And these things are probably not going to go into scikit-learn because they require you to make like choices that are like somewhat arbitrary or heuristic. And scikit-learn doesn't really like to make like magic choices. Scikit-learn wants to be like very general. And so the building blocks for the functionality that are not related to plotting, these will probably all go into scikit-learn, but the way to like just have it work out of the box is probably not going to go into scikit-learn.
All right. Thank you, Andreas. Unfortunately, we have just a little bit of time for this, but at the end of the session, as I mentioned, hopefully we will be able to capture a couple of more questions. Thank you, everyone. Great questions. And then we will continue with our next speaker now. While our next speaker is joining us, I just want to remind you guys that you can keep uploading the questions if you want it to be really answered. I know that we are very limited in time, and we are going to do our best to answer as many questions as we can. And here is with us our next speaker, Monica Bobra, and her talk was titled as Forecasting Solar Flares. And let's get some questions for Monica.
Does the question get zeroed out, or?
Yeah. Okay, I have to get these. Yeah, I get these out. If I delete your question for Monica, please post again, because there's no way to clean them out at once for the previous speaker. All right. So many questions. Okay. Now we're accepting questions for Monica. Okay, while we are waiting, Monica, could you tell us maybe briefly about your talk?
Yeah, sure. So this talk was, as I was watching all of the other talks yesterday on YouTube, a little bit different from the other talks in the session, as it was more of an application rather than a machine learning tool. So I'm a research scientist, and I study the sun, and specifically I study solar flares. So I was talking about various different learning algorithms I've used along with collaborators to predict solar flares. And I guess one thing that really struck out to me when I was watching the talks yesterday on YouTube is Ana Comenciana's talk about feature selection. And I really agree with what she had to say about using a good feature space. So useful, informative features are more likely to improve your predictive models than a complicated algorithm.
Okay. Thank you, Monica. So we have some questions coming in, and I'll be reading them for you. Can you say a bit more about the project where you took into account different solar atmospheric layers? What techniques did you use, and major physics findings?
Yes. Okay. So to give a little bit of context for this question, there are various different NASA satellites that are observing the sun, and we use data from one called the Solar Dynamics Observatory. And it takes images of various different layers of the solar atmosphere, from what we define as the surface to subsequently hotter and hotter layers in various different wavelengths, from optical to UV, and there are also X-ray images of the solar atmosphere. So what techniques did we use? We used the convolutional kernel network on these image data, and the major physics findings were that where the magnetic field of the sun gets quite twisted is those regions are the ones that are most kind of flare productive, I guess. That's a very sort of general high level answer, but that's the quickest answer.
Thank you. The next question is, how do you collect the solar flare data, and is a small subset of data available to explore?
Yes, absolutely. The data are all public. They are available. Probably the best way to get data from the Solar Dynamics Observatory is to use SciPy. So if you go to the SciPy website, scipy.org, there are a few affiliated packages. One is called DRMS, one is called AIAPy, and they're very well documented, and you can pull the data and work with it right away.
Great. The next question is, in your take 3, you said you considered non-independent nature of solar flares in different locations. Could you explain more?
Right. Okay. So in my talk, I talked about these regions called active regions. So you have these areas on the sun that are more flare productive, and then you have these areas on the sun that are quiet. And when NOAA, the United States official space weather prediction agency at NOAA, predicts solar flares, they look at these active regions individually. So each one on the sun is kind of considered independent. And my colleagues and I were thinking that perhaps that's not the best way to look at the problem. So perhaps there's a dependence between all these active regions on the sun. And so what we ended up doing was doing a time series analysis of all the behaviors of all the active regions on the sun at the same time. I don't know if that answers the question, but that is what we did.
Thank you. I'll take one more question and then we'll need to move on. Are there any specific plans you know of to apply the flare? To apply the flare predictions? How accurate does the prediction have to be for the application, if so?
Oh, okay, here it is. Are there any specific plans you know of to apply the flare predictions? I don't quite understand. Oh, you mean like operationally in real time, perhaps?
I think that's what.
Yeah, okay, yes. So in the United States, NOAA issues our weather predictions, like whether it's going to rain tomorrow or not. NOAA also issues space weather predictions. So there are kind of two communities out there. There are people like me that are doing research, and then there are government agencies like NOAA that are actually issuing the official predictions. And there is a whole entire area of research devoted to how to get a learning model from a research stage into an operational stage. And so NOAA is like very heavily invested in that, and NASA is too. So these are kind of research projects in the works where people are figuring out how to do the work that we're doing here at SciPy, research work, and get it working in an operational setting.
Great. Thank you, Mona. This was great. And thank you for your time. And we will be moving on with our next speaker. Thank you. And while our next speaker is joining us today, I think it will be easier if we can maybe just preface our questions with the name of the And our next speaker is Nina Miolaine, and the title of her talk was GeomStats, a Python package for Riemann geometry in machine learning.
Yes. Hello, everyone.
All right. Let's see if you can preface your question with Nina, that would be great. Okay, I see some questions in here. I'll just move them up. Okay. So the first question, as it seems, is this for convex manifolds? Are there any other requirements for manifolds? Are gradient boosted trees as an example of manifold learning? There are a lot of questions here. I'll just let you start.
Yeah. So I will start with the first two ones. So is this for convex manifolds? No, not necessarily. The manifolds that are implemented are listed in the module called geometry. There are actually 15 different manifolds currently implemented. So examples are the manifold of symmetric positive definite matrices, the hypersphere, which is a very intuitive example of manifold, the hyperbolic space, Stiefel manifold, Grassmannian manifold, etc. If you want the whole list, you can go on the GitHub account. And then, are there other requirements for manifolds? Not really. I mean, if you're interested in manifold that is implemented, that's great. If you're interested in adding another manifold, or if you're interested in asking us to add another manifold, there are no specific requirements. So far, the manifolds that are currently implemented often have closed forms in terms of the geodesic equations, for example, the Riemannian exponential or the Riemannian logarithms, which are the generation of the addition and the subtraction on Euclidean spaces to manifolds. But even for manifolds that don't have closed forms for these operations, we have automatic differentiation enabled with AutoGrad and PyTorch and TensorFlow. And therefore, if you have a manifold with no closed form, but you know the Riemannian metric, we can compute the geodesic and the exponential and the logarithm by using automatic differentiation.
Thank you, Mona. Thank you, Nina. The next question is there any way to generate hyperbolic embeddings for images in GeomStats package?
So currently in GeomStats package, we generate hyperbolic embeddings for graphs. We have a function that does it automatically, and we also provide an open source data set, which is the Karate graph data set that is quite known in the graph community. For images, Not that I'm aware of. I mean, we don't have that right now. Would you do it? Because maybe it's straightforward to adapt the code that we have. We just don't have currently an example or notebook that does it. But maybe we can generalize that quickly.
Thank you, Mona. Nina.
That's fine.
Okay. Do we have more questions for Nina? Okay. Are there any plans to work with PyTorch Geometric for PyTorch implementations?
I mean, we're not working on that at the moment, but that's a very good question. The packages we're working on are, for example, PyManopt, which is optimization on manifolds. So we do mostly geometric computations on manifold, which are low-level mathematical operations on manifold. And we also do statistical learning on manifold that can use optimization on manifold. But in that case, we will call another package, for example, PyManopt, GeoOpt, or packages like that. I haven't looked at PyTorch Geometric at the moment, but it is a good idea. And if you want to see that implemented, you can also raise an issue on the GitHub account, and we'll work on that.
Beauty of the open source.
Yeah.
Okay. So I'll take one more question, and then we will move on. I will use point careable model for generating embeddings, perhaps. What do you think?
Yes, that's definitely a good idea, and that's also implemented in GeoMstats. So we also have a notebook that uses the Poincaré-Ball model to embed graphs. And again, the dataset that we use as a toy example is the Karate Graph dataset. So the code is there, and you probably can generalize that to your dataset. And is it a good idea? Yes, hyperbolic embedding for graphs have shown success in machine learning application over Euclidean embedding, for example.
Great. I think we can take one more question because there's some upvotes for it. Can data generate its own manifold, or do you have to specify one a priori?
Yes, so that's a good question. At the moment, you have to specify one a priori. So it's not a package of manifold learning. We don't learn any new manifold. If you know the manifold on which your data are, then you can compute on that manifold and do statistical learning on that manifold, which is interesting because let's say you want to compute the mean or principal components or things like that. You're not looking in a space where your data could not lie. You're constraining your operations on the manifold where you know that your data are. It was a bit linked to the first question, how do you specify your manifold? So either it's one that we already have implemented, or you can implement yours by specifying the Riemannian metric and then use automatic differentiation that we have implemented to get the exponential on the logarithm.
Great. Thank you so much, Nina.
Thank you.
Bye. Okay, so we're waiting for our next speaker to join us. Okay. Okay, I think our next, okay, it's connecting, a little bit lag in the connection, but there you go.
Hello.
Hi, so our next speaker is Joe Eaton, and his talk was titled GPU Accelerated Data Analytics in Python. And we can take questions for Joe. You can post them in the Ask a Question button there and upload. Maybe while we are waiting, Joe, could you tell us very briefly about your talk?
Sure. So my talk was a presentation of our open source accelerated machine learning package called Rapids. And I went through the components of Rapids, CUDA data frames, cuDF, CUDA machine learning, cuML, and CUDA graph analytics, which is cuGraph. and I talked about the goals of the package and some of the performance speedups we're getting, which are in the range of 10 to 100x speedups for common operations you do in Pandas or scikit-learn or NetworkX.
Great. Okay, some questions are coming in, and I will be reading them. How people in the industry prove that two ML models work equivalently, paying attention to the fact that they use approximate floating point calculations. The results are probabilistic and hardware can be different, GPU versus CPU.
Yeah, for example, k-means is one of these type of algorithms. It's hard to prove something when you only have a probabilistic algorithm, right? What you can do is say that the results are inside of a ball of probability. And if you make that ball small enough, it becomes acceptable as a good enough answer. But a proof, there are no proofs for probabilistic things. We only know on average, they do lie in a ball of probability.
Mm-hmm. The next question, GPU. Did you plot analyze how much performance depended on the model of GPU available? Is that available?
Oh, great question. So we do post results for, I think, 3 different GPU models. We use a T4, which is the smallest card. We have things like Quadro cards, so common desktop or workstation cards. And then we also use the high-end data center cards, V100s or P100s. I think we post results for all 3 of those. And generally, the bigger, more expensive cards do a lot better. That's how it goes.
Yeah. Given the excellent performance of Rapids and the apparent ease of using it, when will CPU used in data science become obsolete, or will it not?
I don't think it will become obsolete. I think it will always be a component. Computers now are hybrids, right? Every computer has a CPU, and most computers also have GPUs. I think they're both important, especially for debugging and testing these kind of things. Even on these very small problems, CPUs are still much faster on the smallest problems where you're debugging and testing. GPUs really pay off when you go to larger and larger data sets.
Okay. All right. I think those are the questions we have so far. Thank you so much, Joe, for joining us today. Oh, I have one more. Okay, let's take this one as well. Would you like to see upstream projects like NetworkX, scikit-learn, and Pandas eventually include GPU support on their own? Or do you see it as a better approach to maintain GPU implementation separately?
Yeah, so this is a great question. I think right now we're moving independently. Certainly on the GPU side, we have a lot of ground to make up. The Pandas has been around for a long time and has a lot of features that we don't yet support. It's a very long list of features. Eventually, maybe as we both get mature and the APIs stop changing as much. I mean, Pandas 1.0 just came out. So they were changing the API very, very quickly until very recently. So now that Pandas 1.0 is out, there's a higher chance of us merging with them and getting one repository for everybody. That's out of my, I don't make those decisions, but we can try. Let's see, when will GPU cost per cycle come down? Oh, so that's an interesting question because depends on what you're looking at. But we do a lot of tests of cost per cycle or cost per problem solved, and GPUs are much cheaper in terms of cost per problem solved than CPUs, especially in the cloud where you're paying for time. Because GPU is 100 times faster, it's not 100 times more expensive. And so you're actually winning to pay more for the GPU.
Great. Okay, I think we have time for one last question. Do data science teams you work with ever run into issues provisioning, managing GPU hardware, since companies run most of their software on CPU?
So not as much anymore. It used to be a big deal. Say 3 to 5 years ago, it was a big deal. Hardly anyone had GPUs installed locally. These days, every cloud has them. They're very common these days in the cloud, certainly, and almost every machine you can buy these days has at least a tiny GPU you can use. Yeah, it's not an issue these days.
Great. Okay, let's take this last one as well, Joe. Is there any Unicode string to ASCII OCR applications?
OCR, optical character recognition, I think you mean.
Yes.
I don't think we have those in Rapids. Now, other packages do have image processing. Rapids doesn't do image processing. It's mostly tabular data processing. So if you're looking for image processing, that would be a different package.
Right. Okay. All right. Thank you for your time, Joe.
Mm-hmm.
The next speaker is connecting. There it is.
Hi.
Hi, Jay. So our next speaker is Jay Wonderplus, and his talk was titled JAX, Accelerating Machine Learning Research. And we are taking questions for Jack now. I think this question was for the previous speaker.
Yeah, let me just say a bit about my talk. So I talked about JAX, which is this Python package that basically uses a NumPy-like API to target the XLA compiler. XLA is the accelerated linear algebra that was developed within Google and is used within TensorFlow. And basically what JAX is a flexible framework in order to do very fast operations on GPUs and TPUs, including autograd, automatic differentiation, and it's we're working on it as a useful framework for machine learning research and people who are trying to build new types of machine learning models and want to do it in a very fast and accelerated way.
Very exciting. Okay, the first question is, what's the difference between QPy from Rapids and JAX? What's the use case for each?
So I'm not totally familiar with QPy, but my understanding, and forgive me if I'm wrong, is that QPy is basically a way to target GPUs. JAX is a little more broad. What it's trying to do is create a composable system of basically an API where you can compose different operations as well as transformations like automatic differentiation and just-in-time compilation and target CPUs, GPUs, and TPUs all with the same code.
Thank you. If I'm already comfortable with PyTorch, what are the main features of JAX? Sorry, my screen is just sliding. JAX that would let me do things I can't do with PyTorch.
Yeah, that's a really good question. So one of the things that JAX offers is the ability to kind of define things from the ground up, whereas in often in frameworks like PyTorch and TensorFlow, you'll be using kind of predefined kernels that do things in a very optimized way. And what JAX does is it allows you to essentially define your own kernels without having to go beyond writing Python code. Mm-hmm. That Python code can be compiled via XLA into very fast kernels for essentially arbitrary operations that you want to do on your data.
Thank you. What about interoperability between JAX and Numba?
Yeah, it's a good question. JAX and Numba are really, in a lot of ways, orthogonal to each other. I've seen a few examples of using Numba's fast operations as sort of a component to, sort of working together with JAX. But it's really, like for example, what you could do is you could use Numba to define a very fast operation that's not available in JAX, and also to define a specialized gradient for that operation, and then plug it into the JAX framework, and then JAX would allow you to plug that into everything else that you're doing within the system.
Next question, what restrictions are there on what the JIT transformation can handle?
Yeah, good question.
How are the error messages when something is not supported?
Yeah, so the JIT, as I mentioned briefly in the talk, the JAX's JIT is not like a bytecode compiler like NumPy. It's a little simpler than that, but the framework allows you to do some interesting things. But essentially what JAX's JIT does is it has a predefined set of operations that it recognizes. And these are basically, you can think of them as NumPy array-like operations. And so any of those operations, it knows how to compile. And when I say compile, what I mean is it sort of extracts the set of, it extracts the sequence of operations that you're doing and passes them to XLA, where XLA can do the actual like optimization of that sequence of steps. But if JAX in the compilation phase encounters something it doesn't know how to do, it will generally fail loudly. Like for the most part, you shouldn't get silent failures where your code just doesn't work, but you'll get these loud failures where at the moment that it happens, you know that there's a problem.
Okay, I think we have time for a couple of more questions. Thanks for the great talk. I was wondering what kind of direction JAX is heading. How will JAX differentiate, no pun intended, from TensorFlow in terms of development and usage?
Yeah, it's a really good question. There's some information about that on JAX's website, and there's kind of ongoing discussions about what the future of JAX is going to look like. But right now, what we're interested in doing is just being the best tool for machine learning researchers that we can be.
Great. How well does JAX behave in virtualized or containerized environments?
Yeah, good question. So JAX should work just fine in that sort of environment. If you, for example, if you go into an open Google Colab, which is a Jupyter Notebook front end, it's a containerized thing, and JAX is pre-installed there, and you can use it on CPUs and GPUs and TPUs, without any extra work.
Great. All right, I'll take one last question. Is completion supported for all built-in Python types? When is a function recompiled?
So those are kind of two different questions. I'll address the second one because I have a better answer of that. But when things are recompiled, it essentially depends on how the function is defined. But in most cases, it'll be recompiled if you have an array of a different shape that you put in. So JAX compilation kind of knows how to handle all arrays of a given shape. And if you try to use an array of a different shape, it will likely recompile.
Great. Okay, the last question this time. Do you have a go-to sample data set that you use to test your TensorFlow setup before launching bigger jobs? If so, can you recommend or share?
I don't think I have a great answer for that.
Okay. All right. Thank you for being with us today, Jack, and great talk. And
yeah, thanks so much.
Bye. Okay, our next speaker is joining us. Hi, Jacob.
Hi.
Our next speaker is Jacob Montiel, and his talk was titled Learning from Evolving Data Streams. And we are taking questions for Jacob now. Maybe while we are waiting for the questions, Jacob, could you tell us a little bit about your talk?
Sure. So this talk is a brief introduction to the field of stream learning. In stream learning, what we are focusing on is on a type of data that is continuously being generated. And in this scenario, we are also allowing that data is not going to be stationary. So it's going to be evolving, which in our field is known as concept drift. So there are many scenarios where you will find this kind of data, like logs, network communication, financial markets. And the idea in stream learning is that you basically are going to have a model that can evolve with the data, and it's always on this continuous learning approach. So basically, we don't have phases, offline phases, like in traditional batch learning, where you have training and then you deploy your model. In this case, our model is live, and it's always evolving with the data. Also, in this talk, what I introduced is Scikit Multiflow. Scikit Multiflow is an open source package for doing basically machine learning for data streams in Python. The principles for Scikit Multiflow is that it has to be easy to design and run experiments, and also it has to be easy to extend. So if people are interested in this field and they are working on this field, you can use Scikit Multiflow and the tools that are available there, or you can also work on your own methods or extend existing methods and increase what we have in the field.
Okay, thank you, Jacob. We have a few questions. One question asks, is this ideal for small swap sensors? Can you comment on deploying this on small embedded platforms?
So in nature, some of the methods are going to be very efficient, because one of our main concerns of the requirements that we have is that we have to be very efficient in terms of requirements, both time, processing time, and memory. I'm not familiar with swap sensors, but I know that some people have been able to deploy this for IoT sensors. And there is some people that are actually looking into deploying into embedded, because that's something that is, I think for this field of stream learning, it's very interesting in the sense that we can either have data going through a system or models are going to be learning from the data, or you can have small models in the devices and learning from them, and then you just send the model to some centralized system, which is kind of related to federated learning.
The next question is, once a drift is detected, does the model train from scratch again?
Not necessarily. So once the model is detecting drift, it's going to adapt. So, for example, in the talk in the demo I have in the talk, I talk about having an adaptive tree. That model, what it's doing is that it's a decision tree, and what it's doing is that it's regenerating the part of the branches. So maybe one branch is obsolete for this new concept, and it's going to remove that branch. So it's not removing the whole model, but it's just removing the parts that are not needed anymore or not relevant anymore. So that's the goal, that we don't want to create a new model from scratch, because we would be losing information that might be useful in the current concept. So the idea is that we want to maximize information as much as possible. Sorry, I didn't hear that. I think your mic is muted, or is my mic muted?
Oh, yes. Can you hear me now?
Yeah.
Okay, sorry about that. How does your model keeps up with the trends? Something like negative sampling, or are there any other methods to achieve something similar?
Well, in this sense, I guess for negative trends, it's just part of your data. So your model is going to follow whatever data you are showing it. Of course, in terms of concept drift, if we are talking about concept drift specifically, that we have either like positive and negative trends, a good concept drift method should be able to follow this in both directions, either positive or negative trends, because we're interested in the drift itself, not the nature of it. So there are some statistical tools like Bayesian that you go in only one direction, but there are other alternatives into stream learning community, for example, Adwin, that it can follow both directions.
The next question is, can FFT and filtering can be done using this package?
at this stage, we have not implemented these tools. What we have focused on is in providing interoperability with other tools that may be able to perform these tools incrementally. For example, there are some subset of tools available in scikit-learn that you could use. Mm-hmm. So the idea is that we don't want to be a package for doing everything. And we want to provide something that can operate in the ecosystem of Python. But if this is not something that is easily available and we can look into it, of course, we are open to this kind of changes. So you can go to the GitHub repository that we have and open an issue there, or find us in our Gitter channel and we can discuss this.
Okay. What model interoperability challenges does evolving data streams present?
I think in this sense, it's pretty similar to what we have in batch learning. So there are some models that are going to be easily interpretable. Like I was mentioning, we have the Hofding tree, which is kind of a decision tree, which is somewhat interpretable. I guess the extra element here is that we also have to explain how the model is evolving over time. But other than that, it's pretty similar. Like we can have something more complex, like ensembles that could make interpretability a little bit more complex. But I would say that it's pretty much in the same state as batch learning.
Can you comment on throughput versus non-adaptive algorithms? What's the penalty for retraining? So if you don't have the adaptability part, so let's say that you have an incremental model that by its nature is going to eventually follow the trend of the data. So in this case, what we see is that these models are somewhat faster because they don't have to be looking into the drift. And then you have this trade-off. They are somewhat faster, but then they are going to adapt at a slower rate. So if you change or your data is constantly changing, maybe you want to have a drift detector and then you're going to sacrifice a little bit of throughput, but you're going to be able to adapt faster. Now, on the other hand, if your model or your data is not changing that fast, maybe then you don't need to have this specialized section for constant drift, and then you just go with faster throughput and your data. And also, like, for example, if you have lots of data, and then you say, like, okay, I'm going to give my model a lot of data, and it's going to, that way, enforce the adaptation faster. So it's just a trade-off. Okay. Our last question is, how do you handle learning from streams with highly imbalanced data? Do you have support for sampling from streams?
This is a very important question. It's still an open question in our field. So far, we don't have a specific means to work on it. We have some ideas. There is just starting to appear in the research field that how we can work with streams, with imbalanced data in data streams. So I would say that sampling is one of the cases. Like some techniques are now being adapted from the batch scenario to the stream scenario, and I guess it's a nice opportunity. We are very interested in this topic. We don't have at this point something implemented because the field itself is still working on it. But it's definitely something that is something that it's interesting for our field and for us as a project.
All right. Thank you so much for your time for today, Jacob.
Thank you.
Thank you. Bye.
Hi.
Hi. Our next speaker is Simon Mo, and his talk was titled Machine Learning Model Serving the Next Step. And we are taking questions for Simon now.
Right. I'm also sharing my screen. Can you see it?
I can. Can everyone see? If you can see Simon's screen, can you please say yes?
Right. It does seem like it's appearing on the big screen. Thanks. Yeah, so let me just give a really quick overview of my talk. So my talk is about what happened after you train a machine learning model. And typically the model needs to be put into production. And what do we mean by putting a model in production? It typically means either use a model to sort of score a bunch of data, and this is what we call offline scoring, or you sort of put it in an online interactive use case. This is what we call online sort of serving. And then this RayServe is sort of a new framework we're building to address this online serving use case. And there are typically two common approaches people are using for model serving today. Either you just use the existing web serving system, but this has some issue like no batching or no optimization. And there are another whole suite of solutions are specialized model servers, and they're typically hard to use and hard to learn. And my talk is about a new framework we're building called RayServe that sort of scales your model serving workload to even a cluster of machine, as well as give the data scientist end-to-end control over the model serving API. So, and then I have some links on the page as well as our Twitter account. Yeah, happy to take any question.
Thank you, Simon. The first question we have is, how does RayServe compare to TensorFlow serving?
Right, great question. So TensorFlow serving is sort of what we call on the second category as the specialized tensor in tensor out systems. So typically, if you need to deploy a TensorFlow serving in production, you can put the TensorFlow model in the TensorFlow serving server, but you still need to implement sort of the end-to-end API. And then you're taking the input and you sort of transform the input into numeric arrays, and then that you need to send the numeric array to the TensorFlow serving and then get back, and you still need to do some post-processing. So what happens then is your sort of input output are segmented, and then you need to you don't have the end-to-end control over the API anymore. And in addition, TensorFlow serving is only TensorFlow, and it's really hard to sort of adapt to the modern sort of data science workflow where you use the tool that's best for your problem. So you can have a suite of scikit-learn, XGBoost, PyTorch, and TensorFlow all in one, sort of a part of your serving models.
Thank you. Any more questions for Simon? Can you serve a model zoo portal where multiple models available at once?
Right, great question. So RayServe can actually serve arbitrary Python models. So we have a very flexible API, more in that in the talk, and then so we can sort of proxy any request as well as basically serve arbitrary Python sort of procedures. So yes, definitely we can serve model zoo, we can serve protos, we can serve, and more importantly, multiple models available at once. So because RayServe has this capability of managing multiple models and then even multiple versions of the model, they actually make a great choice for sort of serving model zoos. And on top of that, RayServe has the ability to sort of scale a model replica, that's what we call. So you can have a model, and when that just one single model is not enough to handle the traffic, you can scale it to hundreds of replica of that models to sort of handle the incoming web traffic.
And I think this is a follow-up to the previous question, also reinforcement learning.
Right, indeed. So RayServe, because we have this kind of ability to serve arbitrary machine learning models, we also have support for reinforcement learning. So also as sort of like, because RayServe is built on array, you might be familiar, if you're familiar with reinforcement learning, you might be familiar with a library called RLib, which is like built on top of Ray to provide best-in-class sort of reinforcement learning library support. And we are working closely with the RLib developers to sort of have built-in support to sort of serve the policy.
Okay. Is RayServe a web application server framework like Flask, or a way to create an API using some other web server?
Right. So I actually call it a web framework because you're actually given an API to directly access to the HTTP request. So you can basically, for when you're implementing a RayServe service, you have the end-to-end control just like Flask. And however, we actually scales your web serving across multiple machines. So it's kind of different from Flask, where the Flask is only constraining a single process, we actually can span across multiple machines with hundreds of processes.
Can you secure served models with a token?
Right, exactly, because we have this kind of end-to-end control over the API, you are sort of free to use what kind of authentication protocol or security protocol you would like. And then you can use, we have tried to, one of the users have used basic authorization token, and that worked out greatly.
Great.
Yeah.
Last question. Do you have plans to build monitoring tools for RayServe?
Right. So this is exactly sort of in the work right now. In particular, we have basic monitoring support as well as basic export for Prometheus sort of format. However, we are sort of looking into specific use cases. We'll want to work with users, or especially users, to sort of think about how can we best hook into your monitoring solution? What are some of the best formats for monitoring? As well as like how can we best do sort of user-defined metric and sort of do model monitoring specifically, that sort of given a model in production, how do we know the model is sort of how do we know that model is have degraded performance and then it's in time for retraining?
Thank you, Simon. Unfortunately, we will have to move on.
Yeah.
Thank you so much for your time today and for being with us.
Thank you, everybody.
Bye. Hi, Niels. Our next speaker is Niels Ventolin, and his talk was titled Pandera, Statistical Data Validation of Pandas Data Frames. We are taking 4 questions for Niels. While we are waiting for the questions, Niels, could you tell us a little bit about your talk, just to refresh our audience's memories?
Yeah, sure. So I guess the problem that I set out to solve with Pandera was I use pandas a lot at work, training machine learning models. And kind of I noticed a lot of kind of silent bugs go through my data frames before I was training the models, like so using PyTorch or sklearn. And I just really needed a way to validate the types and certain statistical properties of the data before sending them off to potentially long-running training jobs. So really the main use case I had building Pandera was to catch these kinds of errors early on in the pipeline and to kind of help debug those types of errors.
Great, thank you, Niels. We have a question. Can I say hypothesis testing on set of data a form of data validation technique?
Yeah, so the hypothesis testing API of Pandera is a little bit, I would say it's kind of experimental, because another use case I have kind of at work, I'm a ML engineer at Talkspace, which is like a mental health platform, is we do kind of some very small scale analytics projects. So things like, yeah, I guess I can't talk too much about it, but yeah, things like, you can think about them as like A/B testing and very simple like t-tests. So I guess I don't know where to like categorize that exactly, but the workflow I'm thinking about here for using hypothesis testing is at the end of the notebook, I have some kind of data frame that I'm saying, the mean value for some variable is higher for one group versus another. And I just want a way of asserting that as part of my data frame schema. That's kind of like after all the data processing has happened. So I guess you can call that data validation, but it's, I guess, hypothesis testing more strictly.
Can Pandera be used with unit testing frameworks like hypothesis or PyTest? And a related question.
Yeah, that's a great question. So this is actually kind of an issue on the Pandera GitHub right now for generating samples given a schema definition. And sort of my thoughts on this is to use hypothesis, the hypothesis package for property-based testing. You can use this for PyTest. So for example, if you have, this isn't the talk, but you can decorate your functions. Like say you have a data preprocessing function, you can decorate the inputs and outputs of that function with a schema. So you can sort of guarantee that it passes those validation checks. And you can test those decorated functions in just a general, or in a PyTest framework.
Can Pandera infer validations from a known good data frame?
Yeah, this is also a very new experimental feature where it's super basic right now. All it does is infers data types and I think min-max values for continuous variables. But the thought is, yes, to infer a schema from a known good data frame. And then there are serialization tools for outputting the schema as a YAML file or even as a Python script. The way I use it at work is really to define the schema in a Python module and then import it and reuse it in various other places, like in tests or in the actual business logic of the application. So yeah, there is a plan to make that schema inference a lot more robust and have different levels according to the use. The details are TBD for that.
Okay. All right. Thank you, Niels. If you don't have any more questions for Niels, we are going to try our next speaker again. All right. Thank you.
Thank you. Thank you.
Like it is expected in any virtual meeting and conference, we are having some small technical issues, but we will be continuing with the remaining of the schedule. Okay. Okay, our next speaker will be Robert Nishihara. If you are here, could you please wave at us, Robert, because I'm not able to find you among many other Roberts. Thank you, Rich. Okay, if Robert Nishihara, if you are here, could you please wave in the chat so I can find you? It seems like, okay, there you are. Okay, great.
Hey, can you see me?
Hi, Robert.
Hi, nice to meet you. Thanks for having me.
Thank you for being here. Our next speaker is Robert Nishihara, as I mentioned, and his talk was titled Ray, a system for scalable Python and ML. And we are taking questions for Robert.
So I just posted a link to Ray in the chat in case people want to take a look at the GitHub. And while we're waiting for questions, I can also say just a little bit about, Ray is an open source project. It's for scaling Python applications, and it's sort of got two parts. There's the low level library for scaling arbitrary Python applications from your laptop to a cluster. And then there's also an ecosystem we're building on top of Ray for scalable machine learning. So that includes libraries like for hyperparameter tuning, reinforcement learning, training, and things like that.
Great, thank you. Before I move to the first question that I'm going to take, I think I, by mistake, deleted somebody's question without being answered. If you hear me, please post your question again. I will try to get to that as soon as we can. Okay, the first question we have for you, Robert, is does Ray support running containerized tasks? And how does it relate to DAG based on distributed workflow like Airflow or SnakeMake?
Yeah, that's a great question. So right now, when you can, no. So Ray doesn't support running individual tasks in individual containers yet. That's actually something that is something we're planning to do, but it's hasn't been done yet. And that, this comes up when it's actually important in a lot of settings, like in the more multi-tenancy setting, when you have, different applications or different jobs running on the same cluster that might have different library dependencies or things like that. So that's something that's very much on our radar. And then for things, how does Ray compare to Airflow? That's a really good question. They're different in terms of the, Airflow they're different in the terms of the kind of granularity of tasks that they're supporting. Airflow is typically, taking multiple different jobs and kind of stitching them together. And Ray is often taking a single application and scaling that up across a cluster.
Thank you. How does Ray handle varied compute resources and acceleration? Specifically, how does it map job resources to compute instances?
Yeah, so that's another great question. So a typical job might use CPUs, it might use GPUs or TPUs, or some tasks might require a ton of memory, or some data set. So they're all different kinds of resources that are relevant. And Ray has two things. It has a scheduler, which assigns different tasks or actors to different machines. And it has an API that lets tasks or actors specify their resource requirements. So in the, if you're using Ray, the API lets you decorate different functions or classes and say that this, this task requires 1 GPU or half a GPU or a certain amount of memory. And then machines can also specify the resources that they have available. So a given machine can say that it has 2 GPUs or that it has a particular data set, and then the scheduler will map those, handle that together.
Mm-hmm. How does Ray handle data in cloud object storage?
So the assumption, I think if by cloud object storage you mean like S3 and the equivalents from other cloud providers, So basically, we provide one of the nice things about Ray we're trying to achieve is letting it integrate with the existing ecosystems that people are already using. So if you have your data in S3, it's easy to read that data, spawn a bunch of tasks or actors that read that data from S3 or write to S3. And so that's something that, is a pretty common use case or pattern. Oh, sorry, you're muted right now, I think.
Sorry about that. Okay, I missed the question, but I will get back to it. How does Ray compare to Dask?
Oh, great question. So I'm sure most of you guys are familiar with Dask. There's sort of, in both cases, there's like the core system, Ray and Dask, and then there's the ecosystem of libraries built on top. So I can compare on both of these different fronts. If you're talking about just the core system, if you look at the APIs, the low-level Dask API and the low-level Ray API. So the Dask API is most similar to the Ray remote function API for scaling Python functions. And the big differentiator here, at least from my perspective, is Ray's support for stateful computing through actors. Which is how we translate Python classes into stateful services running in a cluster that can have mutable state. And that's actually something that Ray didn't initially have an actor API. But when we started to try to support workloads like reinforcement learning or stream processing, we ran into limitations. And, because these single-threaded applications typically use functions and classes, then to be able to scale this up, it's important to be able to translate both the functions and classes into the distributed setting. So in this way, Ray actually has some similarities to tools like Erlang or Akka or even RPC frameworks like gRPC. So that's on the core system side. In terms of the ecosystem, Dask has support for libraries like data frames, scalable data frames, collections. And so in some ways, there's actually a natural comparison between Dask and Spark because both of them have high quality data frame libraries. In terms of the libraries that we've been focusing on with Ray, it's really targeting scalable machine learning. So that while the Ray API itself is very general, very flexible, the libraries we've been building are targeting things like machine learning training, reinforcement learning, deploying machine learning models in production, hyperparameter search. So those are some of the big items. I think there are tons of other differences like architecturally and things like that, but one thing is that Ray actually supports, has started to support other languages like Java and C++. But in terms of the main differences for users, I think it's about the libraries and about the actor API.
Great. How is Ray funded?
So, great question. So we started out Ray, in grad school. I was doing a PhD and along with other people. So I guess initially it's funded by Berkeley, by the NSF and organizations like that. We recently started a company where we're continuing to develop Ray called Anyscale. And so that's the main source of funding now.
This seems to be a follow-up question. Does Ray use Slurm or Torque then for job scheduling and resource mapping?
So Ray itself, it doesn't use Slurm, but you can, if you have a Slurm cluster, if you're using Slurm, then you can submit Ray applications to your Slurm cluster and run. It's similar to Kubernetes, right? If you're using a cluster manager like Kubernetes or Slurm, then you can submit Ray applications and run that on top. So we have a number of users doing that, and one of the things we're trying to achieve with Ray is letting you run Ray applications anywhere. So that could be on Kubernetes or Slurm or your laptop or any cloud provider like AWS or GCP or Azure and so on.
Okay. All right. Thank you, Robert. We are running a little bit out of time. Good thing this is like a little bit break before the lightning talks, but thank you so much for being with us.
Yeah, thank you. And thanks for all the great questions.
Thank you. Bye. With that, I will try to bring in our last speaker where we had a problem a couple minutes ago. Hopefully this time it will work. And I know we are a little bit off our time right now, but thank you for being here, guys. There she is. Hi, Hannah.
Hi, I'm sorry about earlier.
No worries, no need to apologize. So our next speaker is Anna Komasana, and the title of her talk was Optimizing Humans and Machines to Advance Science. And we are taking questions for Anna. All right, so maybe while we are waiting for the questions, you could tell us a little bit about your talk, Anna.
Yeah, absolutely. I'm working on a project that tries to predict molecule properties based on molecular structure. And so we ran into a pretty big problem when it came to feature selection. One, because we had a lot of correlated features, and two, because we had, a lot of mixed type data. And so we looked into different types of feature selection methods that would keep interpretability of the model and of what features are being used. And my talk was just about that, about different types of feature selection methods and some pros and cons of each type.
Questions for Anna?
If there's no questions, I did notice a comment on the video. Oh,
there's actually a question. Let's get to that. And then with fear of overfitting, feature selection is crucial. How does accuracy of algorithm can be improved with reduced features?
Yeah, I mean, a lot of times what will end up happening if you have too many features and a lot of irrelevant features is that your model is going to, because of a randomness aspect of it, it's almost going to use features that aren't going to be great for predicting. It's going to be overwhelmed by too many features. And so reducing the features will, one, improve accuracy, and in turn also reduce overfitting, because it's going to be less, if you think about, polynomial, if you have less features, it's going to be less, have little, little mounds and little things like that. I'm not sure if that answered your question specifically or not.
The next question is, can you talk more about selecting highly correlated features?
Okay, yeah, absolutely. So if I'm understanding correctly, this question is talking about kind of down selecting features so that they are no longer correlated. And that's definitely a problem that we ran into. And something that we did was use filter methods. And we looked at, Spearman correlation coefficient as well as Pearson. And you have to try out different thresholds. For example, we will eliminate one of two features that are correlated by more than 0.9. And, try different thresholds and figure out what is best for your data.
Okay. One last question. What would you say to someone who says, I don't need feature selection, I can use AI to learn the representations?
And that's something that I've heard a lot. I do think that, feature selection is something that is kind of overlooked. And I think that because we have to worry a lot about the randomness aspect, especially if we're not completely understanding, how neural networks work, for example, or how they're making the decisions as they're making, I think that having relevant features and reliable features that are going to work is really, really important.
Mm-hmm. Okay, I think I'm going to let one more question come in, and then we will have to end our session. This may be a pragmatic question, but how have you handled reconciling surprisingly important features versus the scientific expectations?
Yeah, that's actually really, really interesting. What we're using right now actually is, for example, we have yield suiting index, which is a property of molecules, and we have found 7 molecular descriptors that were really, really good at predicting that. And what we're doing now is looking at those descriptors and looking at what they represent and trying to figure out and make sense of why they were chosen, why they work so well. And so in a way, the results from the machine learning are being used to do more research and to look into why that would be from a physical perspective.
All right. Thank you so much, Anna. And I know we had some issues, but thank you so much for the connection.
Yeah, of course. I'm so sorry about that.
No problem. That's okay. All right, everyone. This marks the end of our session. Thank you so much for your patience and for your great questions. I also would like to thank all the great speakers for their amazing talks and all the information they provided for us today. Again, thank you so much, and I hope you enjoy the rest of SciPy 2020.